morning, ladies and gentlemen. My name is Anne-Carole Honfoga. I'm a PhD student from Mons University in Belgium and University of Abomey-Calavi in Benin. I'm here to present the paper about analysis of channel uncertainty on OFDM and FBMC DVB-T2 simulations. This work is undergone in the context of DVB-T2 system performance analysis in presence of channel uncertainty measurement. With the advent of digital broadcasting, many standards have been developed in the world. Among them, digital video broadcasting terrestrial first generation or digital video broadcasting terrestrial second generation standard are the most adopted or deployed in Africa and Europe. In particular, in Europe, in Belgium, DVB-T is the standard deployed and the switching to DVB-T2 is foreseen. In particular, in Africa, due to the fact that most of African countries took a time in the migration from analog to digital, many of them developed DVB-T2. It is the case of the Benin where DVB-T2 is developed. Also, in Belgium, two main broadcasters exist. There are the Flemish Broadcasting Organization VRT and Radio Television Belge Francophone RTBF, which is used in the French part of Belgium and the Flemish Broadcasting Organization in the Flemish part of Belgium. We have the possibility to work with the Radio Television Belge Francophone. Indeed, the channel is the unpredictable element which is characterized by propagation effects, inducing fading. It determines the system performance and its knowledge is required in the system designing parameters. In order to identify the channel, two main methods are used. There are power delay profile measurement and power delay profile prediction. During the power delay profile measurement, error may occur. Then, in this work, we developed a simulator of a light version of DVB-T2 system, including the main blocks, low density parity check coding, quadrature amplitude modulation mapping, orthogonal frequency division multiplexing, and faded channel PDP recorded by RTBF. We developed also a simulator of an improved DVB-T2 version using filter bank multi-carrier instead of OFDM. We simulated and evaluated system performance using bit error rate versus signal to noise ratio, modulation error ratio versus signal to noise ratio, and error vector magnitude versus signal to noise ratio. The main practical conclusions are: uncertainty is value tolerable for a good signal quality using the quasi-error-free criteria are between 0.1 dB and 0.5 dB in power and 10 and 15 nanoseconds in delay. These values are identified for both DVB-T2 system and FBMC-based DVB-T2 system using 8K modes, 16 QAM and LDPC code rate 1/2. DVB-T2 presents many advantages than DVB-T. DVB-T2 is a flexible and scalable system which capacity increases by 30% compared to DVB-T and allow the system to be closer to the channel limit. It integrates many advanced signal processing techniques like LDPC coding, rotated constellation, spatial diversity technique, and we have many coding and modulation technique parameters which allow this system to have, which allow broadcaster to have a flexibility of choice of parameters. Apart, beside the portable and rooftop antenna reception used in DVB-T, we have mobile reception which is also used in DVB-T2. And DVB-T2 is characterized by a wide network coverage with the channel with deep fading. All of these advantages allow this system to have many research interests in the literature. Many researches have been undergone on DVB-T2 to improve its performance. Recently, FBMC have been proposed as an alternative to OFDM in DVB-T2 to improve its spectral efficiency and performance gain. In this work, the goal is to analyze the channel uncertainty measurement in DVB-T2 and FBMC-based DVB-T2 simulations. I present on this slide the block diagram simulated. Note that the bits are randomly generated, which undergone LDPC encoding, QAM mapping, and inverse fast Fourier transform operation, and cycle prefix is added. The signal obtained undergone the channel effect and the noise is added, and the reverse operations of operation performed in emission are performed. When FBMC is inserted instead of OFDM, we have offset quadrature amplitude modulation, pre and post processing, which are performed in emission and in reception. Also, instead of cycle prefix insertion, we have polyphase network filter, which is used. In order to insert the uncertainty values, the uncertainty values are inserted on the channel power delay profile. Note that two main equalizers characterize FBMC complex finite inputs one-tap and three-tap equalizers. On this slide, I present the input response and the frequency response of the filter used in FBMC. Note that the main parameters which characterize FBMC is the overlap spin factor, which increases with the system performance. One can note on the frequency response of the filter that when the overlapping factor increases, the filter is very selective in frequency. This allows to reduce the out of band power leakage compared to the frequency response of OFDM push shape, rectangular push shape, where the side lobe level is very high. Instead of using QAM symbol, complex symbol in OFDM, real symbols are used in FBMC. Note that normally each symbol is transmitted on each subcarrier in OFDM, but in FBMC, real symbols are transmitted in the half during the half of the symbol period used in OFDM. This allows to achieve the spectral efficiency foreseen in OFDM. And using these techniques, Data can be converted without the effect of the filter thanks to the near perfect reconstruction technique used at the receiver side. During our simulation, the first step was to identify the power delay profile recorded using a test receiver EFA model 4043, and we identified the resolution parameters such as plus or minus 10 nanosecond in delay and plus or minus 0.1 dB in power. We randomly generated these values in power, in delay, and we stabilized the generator of the input step of each tap of the channel, and after that we increase the uncertainties value up to plus or minus 1 dB in powers and plus or minus 100 nanosecond in delay. The main criteria considered to identify the uncertainty value tolerable is the fact that when the losses in terms of SNR are considerable negligible, when this value is lower than 0.1 dB. The main parameters used during simulations are presented here, where one can note that cyclic prefix 132 is used in OFDM case, and the overlapping factor K equal to 4 is used, and the power delay profile used is that recorded by RTBF. The simulation results are presented here in the case of OFDM, and this figure presents the bit error rate evolution in function of signal to noise ratio. One can note that the curve in black color represents the curve without uncertainty, and the other curve are the curve with uncertainty. One can note that the performance decreases with the increases of uncertainties value. And when we use FBMC, we have the same case. The performance increases with the uncertainties value, and at a bit error rate of 10 to the power minus 7, we recorded the value of the signal to noise ratio, and we identified that the losses induced by uncertainties value compared to the curve without uncertainty are presented in this table, where one can note that for plus or minus 0.5 dB in power, plus or minus 15 nanosecond in delay, we have the losses which is equal to 0.13 dB in OFDM and 0.18 dB with FBMC. This allows to conclude that the power and delay uncertainty values in the range of 0.1 to 0.5 dB and 10 and 50 nanoseconds are acceptable values during the measurement for both OFDM and FBMC based DVB-T2 systems. Instead of using the bit error rate, we also use the modulation error ratio and the error vector magnitude versus signal to noise ratio, and we identify that the EVM is well inversely proportional to MER as stated by theory. Also, the increase of uncertainty value does not affect the EVM and MER performance. However, there is a saturation effect of MER values for SNR value above 16 dB. In the case of FBMC, we have the same behavior. Note that EVM is inversely proportional to MER, and the increase of ostentative values does not affect the EVM and MER performance. This saturation effect identified in the case of OFDM is shown also here, but after above 60 dB, above 50 dB instead of 60 dB in OFDM case. This difference is due to the near perfect reconstruction technique used in FBMC for the filter design. In conclusion, we developed a simulator of a light version of DVB-T2 system, including the main bond blocks like LDPC, QAM, orthogonal frequency division multiplexing, and PDP recorded by RTBF. We developed also a simulator of an improved version of DVB-T2 using FBMC instead of OFDM. We evaluated and simulated the system performance using bit error rate versus signal to noise ratio, MER versus signal to noise ratio, and EVM versus signal to noise ratio. The main practical conclusions are uncertainty is value tolerable for a good signal quality using the quasi-error-free criteria are between 0.1 dB and 0.5 dB in power and between 10 and 50 nanoseconds in delay. These values are identified for both DVB-T2 system and FBMC-based DVB-T2 system using HK mode, 16 QAM, and LDPC code rate 1/2. Thank you for your attention.